Alright, so today I'm going to talk about transient recovery voltage, which is a subject that I don't think comes up very frequently in our group, and I don't think it's well understood in our company. But it's an extremely important concept to understand when it comes to specifying breakers for projects. We typically specify breakers just based on voltage class and interrupting current, but that's a bit of a misconception because the interrupting current rating of a breaker, weirdly enough, doesn't really tell us how much current a breaker can interrupt. It more so tells us the amount of transient recovery voltage that a breaker can withstand after interrupting a certain amount of current. So the main purpose of this presentation is to kind of reframe how you think about specifying breakers, less so based on the interrupting current that the Aspen model tells us, and more towards specifying them for specific applications. So what is transient recovery voltage? Transient recovery voltage occurs whenever a breaker is breaking current, whether it be normal operating current or fault current. It's the voltage that appears across the breaker contacts immediately after the current is interrupted. So if you could take a voltmeter and measure across the contacts of the breaker, on one side you'd be measuring the system voltage, and on the other side you'd be measuring the voltage from the trap charge on the line. And the potential difference between these two points is the transient recovery voltage. Now, what happens inside the breaker leading up to the transient recovery voltage? When the breaker's closed before the current is interrupted, the voltage across the contacts is 0 volts. As soon as the breaker contacts separate, as soon as they lose contact with one another, you get an arc between the contacts that will persist until your AC current sinusoidal switches polarities from positive to negative or negative to positive. As soon as it crosses the 0 axis, the arc will extinguish. And as soon as the arc extinguishes, you immediately see voltage appear across your contacts. Now, at steady state, this voltage is going to be your system voltage, but in the immediate aftermath of the arc extinguishing, it's going to be transient in nature, and the TRV rate of rise has to be withstood by your breaker contacts. So once the arc quenches, the TRV has 2 stages that the breaker has to be able to withstand. The first stage is the thermal phase of interruption, where during the first few microseconds after the arc is quenched, there is still all this heat energy and molten metal between the contacts that has to rapidly dissipate, or else there's a possibility that the arc can reignite. An arc reignition is not to be confused with a restrike. Reignition is defined as being only a partial discharge of an arc across your contacts that is less than a quarter cycle. And it acts to discharge the stored energy in the capacitances in the immediate vicinity of your breaker contacts. If a reignition occurs, then you start the thermal phase of interruption over again. But if you make it through that, if your breaker makes it through the thermal phase, you move on to the dielectric phase of interruption, where in this phase you have a race condition between the transient recovery voltage rate of rise, which is it's increasing steadily, and your insulation strength between your contacts as they continue to separate. If the transient recovery voltage ever exceeds the dielectric strength of your contact insulation, then you can get a restrike. Now, a restrike is a self-sustaining arc that may not be able to be interrupted before doing significant damage. The type of insulation in the breaker also plays a role in this. Oil breakers tend to have less severe TRV rates of rise due to the post-arc currents across the contacts, while SF6 breakers and vacuum breakers have more severe TRVs because they don't experience this and are more prone to current chopping. The nature of the transient recovery voltage in terms of its shape and magnitude are determined by the lump system impedance and magnitude of the fault current. So the lump system impedance being essentially the inductance and capacitance of your equipment that's in the immediate vicinity of your breaker. Anything bus capacitance, CCVTs, shunt capacitances, transformers, series reactors, generators, all those things tie into how your transient recovery voltage is going to behave. You can typically reduce these inductances, capacitances down to a parallel RLC circuit to determine whether your TRV is going to be overdamped or underdamped. Underdamped being worse than overdamped. Underdamped conditions are going to result from high inductances. So typically transformers or series reactors are going to result in underdamped TRVs. Overdamped TRVs, just as a rule of thumb, occur whenever there's at least two parallel lines on the unfaulted side of the circuit breaker. When there's at least two parallel lines on the unfaulted side of the circuit breaker. Overdamped TRVs tend to be less stressful on your breaker as it interrupts the fault. This is typically because it drives the voltage to the normal operating voltage much quicker than underdamped. You do still have to be wary of reflected waves, reflective voltages from the end of the line. If in the case of interrupting a fault, you can still get an underdamped case that has a severe TRV if there is a large reflected wave coming from the remote end of the line. Underdamped TRVs occur whenever a fault is fed directly by a transformer or a series reactor and there are no transmission lines in parallel to dampen the surge. Underdamped TRVs result in oscillatory behavior with higher per unit voltages. The oscillatory behavior acts to extend the amount of time that your breaker is stressed, and the higher per unit voltages tend to just stress your breaker more and increase the likelihood that you're going to get a restrike or a reignition. Typically, if you've got an underdamped TRV, you want to limit your fault current between 10 and 30% of the breaker short circuit rating. So in the case of a high side transformer breaker that's going directly to a line, you'll want to limit the fault current. You'll want to check to make sure that the fault current of that line does not exceed 30% of the interrupting rating. Otherwise, you might have a TRV issue. A few times to consider a transient recovery voltage. Fault interruptions tend to produce the most difficult TRVs as opposed to load switching or even load rejection. IEEE C3711 specifies 3 line to ground faults to be considered instead of 3 line to line faults. So if you're looking at the maximum short circuit rating on a line, the 3 line to line fault is almost always going to be greater than the 3 line to ground fault. But since 3 phase line to line faults occur next to never, you end up using the 3 line to ground fault as your your maximum fault current, just because of the likelihood. Shunt reactor switching behaves very similar to series reactor switching. It tends to just have very large inductances that result in very large transient recovery voltages upon breaking current. Faults occurring immediately after transformers. So the main scenario where this occurs to me to be an issue would be, really high side breakers on transformers, where there isn't any appreciable capacitance between the transformer and the breaker. So if there's no CCVTs, if there's not extensive bus work between the transformer and the breaker, the transformer is going to act as a large inductor in that situation, and there's not going to be enough capacitance to drive the transient voltage to be overdamped. Faults on either the line side or the bus side of series reactors have very high rates of rise. Short line faults associated with high fault current exceeding 90% of the breaker rating have high rates of rise as well compared to terminal faults. So that's going to be close-in faults associated with currents exceeding 90% of the breaker rating, as opposed to terminal faults on the remote end of the line are going to have higher rates of rise. And then any interconnection point, out of phase switching, load rejection can result in very large TRVs. So ways to mitigate TRV: you can add capacitors. Adding capacitance just works to drive the system to be overdamped. So bushing capacitors, shunt capacitors on a bus, CCVTs, capacitors placed in parallel with a transformer series reactor also works. You can uprate existing breaker fault current rating. So that's what we're doing in the case of Trimble County. We are simply uprating a breaker from 50 kA to 63 kA to mitigate a TRV issue. What that entails, though, is changing out the nozzle of the breaker and adding bushing capacitors. There's a lot of 50 kA breakers, older 50 kA breakers, that on their nameplate they say they'll be dual rated 50 kA/63 kA. It's going to be 50 kA or 63 kA with bushing capacitors. And that's what I'm trying to drive home. It's really not the fault current that's limiting these breakers. It's when you're changing out the nozzle, when you're uprating a breaker from 50 kA to 63 kA, you're not changing out the bushings. You're not changing out any of the conductive components of the breaker except for the nozzle. So it's really not the current that is driving the change of this breaker. It's the transient recovery voltage. That's the limiting factor of the breaker. You can also have definite purpose circuit breakers for fast TRV rise times. I don't really know what all that entails, but they have a whole IEEE standard for it. C3706 goes into and you can order these, I guess, for very specific scenarios. So the key takeaways that I want everyone to know from this is the short circuit breaker. The short circuit rating of a breaker ultimately determines the TRV capability of the breaker. But the TRV capability of a breaker really is the limiting factor of a breaker's ability to interrupt a fault. If series reactors or transformer limited faults approach 30% of the breaker short circuit rating, you should consider TRV mitigation. You should probably consider doing a TRV study as well. And then the last thing, if you have a terminal fault or a close-in fault that exceeds 90% of the breaker short circuit rating, you should also consider TRV mitigation, or possibly even a study in those situations as well.